to talk about light and energy and how to use equations to solve for them. So first let's go over light. Light has wave-particle duality, which basically means that light can behave as a wave or a particle. So when we're calculating light, there's a few things that we need to know in order to use the equation. The first one is wavelength, which can be represented with lambda, and it's the distance between the two crests. So if you were to draw a wave, it would be from top point to top point. And that we calculate in meters or nanometers. Next we have to understand frequency, which can be represented with nu. It is the number of wave cycles to pass per unit of time. So that can be in hertz, and hertz is the same thing of the inverse of seconds. We also have to know what the speed of light is. And that can be represented with the letter c, and is equal to 2.998 times 10 to the 8 meters per second. So the light equation that we have to know is c is equal to lambda mu. So let's try an example problem for light. So we want to calculate the wavelength of radiation with a frequency of 8.0 times 10 to the 14th hertz. So we have our equation, c is equal to lambda mu, and we're solving here for wavelength. So what we want to do is solve our equation for wavelength. So we have 2.998 times 10 to the 8 meters per second divided by our frequency, which is 8.0 times 10 to the 14th hertz. And that's going to give us an answer of 3.7 times 10 to the negative 7 meters. So one thing that you should always try to do is make sure to rearrange the equation to solve for what the question asked you for. So why don't you try this one on your own? Violet light has a wavelength of 4.10 times 10 to the negative 12 meters. What is the frequency? So I have the answer up here for you, which is 7.31 times 10 to the 19th hertz. Make sure you get the same answer. If you don't, try it again, and if you still don't understand it, you can come with questions. Next, we have to go over energy. So the light emitted by an electronic transition from a higher to lower energy level has a frequency directly proportional to the energy change of the electron. So basically, when light is emitted, it's equal to the energy change that the electron goes under. So the equation that we have to know for energy is E is equal to H nu. So E is how we represent energy, and that's in units of joules, which could also just be written as J. And then H is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. So that's just a constant that we're going to have to know. And then frequency, which was also used in our light equation, is still measured in hertz. So let's try some example problems. Calculate the energy of a photon of radiation with a frequency of 8.5 times 10 to the 14th hertz. So we're going to write our equation down. E is equal to H nu. And here we're looking for energy, so our equation's already set up like that. So now we just have to plug in our numbers. So E is equal to Planck's constant, which is 6.6 times 6.626 times 10 to the negative 34 4 hertz times our frequency, which was given. Planck's constant is not in hertz, it's in joules times seconds. And our frequency is in hertz. So our energy equals .6 times 10 to the negative 19 joules. Alright, so let's try this one on your own. Calculate the energy of a gamma ray photon whose frequency is 5.02 times 10 to the 20th hertz. The answer that I got here was 3.33 times 10 to the negative 13 joules. Make sure you get that same answer. If you don't, try to look over it again. And if you still can't come to the right answer and don't understand it, we can go over it in class. Alright, so these next two problems are going to put together the two equations that we were dealing with for light and energy. Calculate the energy of a photon of radiation with a wavelength of 6.4 times 10 to the negative 7 meters. Okay, so first let's write down both of the equations. So we have C is equal to lambda nu, and we also have E is equal to H nu. So we're looking for energy, so that's what we're looking for in the end. But it gives us a wavelength, and there's no wavelength in this equation. So what we're going to have to do is use our wavelength to solve for frequency and then plug that into the energy equation. So we're going to have to rearrange this equation to solve for frequency. And then by doing that, we can easily plug in the speed of light over the wavelength, which was given, to give us a frequency of .7 times 10 to the 14th frequency. We're dealing with hertz. So then we're going to take our frequency and plug it into the energy equation. So E is equal to Planck's constant times our frequency to give us an answer of our energy equals 3.1 times 10 to the negative 19 joules. So let's try this next one on your own. What is the energy of light whose wavelength is 4.06 times 10 to the negative 11 meters? Remember, for this you're going to have to use both equations, manipulate it so that you can get enough information in order to plug into your energy equation to get the answer. So the answer that I got here was 4.89 times 10 to the negative 15 joules. Make sure you get that. If you don't, try it again. Maybe another time because this is a little bit more complicated. Then if you don't understand it still, bring questions in and we can go over it in class.